So let's look at our alkenes. So we are going to start with preparation of alkenes. So alkenes are produced by elimination reactions. And there are two main elimination reactions used to prepare an alkene. So the two reactions that we use are dehydration of alcohols and then something called a base-induced elimination of a hydrogen halide from a monohaloalkane. Now, at the moment, that sentence probably doesn't seem to make an awful lot of sense. There's a lot of words, base-induced elimination of hydrogen halides from monohaloalkanes. And at the moment, we don't actually know necessarily what a lot of those words actually are. But what I will do is I'm going to draw a diagram of that reaction. And then when we go on to look at monohaloalkanes, which we will do, we've got 3 lessons on monohaloalkanes, we will visit it again. And at that point, it will start to make an awful lot more sense because you'll have more knowledge and you'll have a better idea about what all of these different things are. So we're going to look at both of these methods of preparing an alkene. So the first method we've got is dehydration of alcohols. So to dehydrate an alcohol, the alcohol vapor is passed over hot aluminium oxide or treated with concentrated sulfuric acid or concentrated phosphoric acid. Now, it's not enough at advanced higher to be able to identify a type of reaction. We also need to be able to identify the chemicals or reagents that we would use in order to make the reaction happen. So if we wanted to dehydrate an alcohol, we would need to know one of the 3 reagents there that we could use to dehydrate it. So either hot aluminium oxide, concentrated sulfuric acid, or concentrated phosphoric acid. And in industry, the use of concentrated phosphoric acid is preferred as less side reactions occur with this acid. So we are going to look at an example, which is the dehydration of butan-2-ol. Now what I would do is just wait until I have drawn this diagram out before copying it down for yourselves, because it will take up most of the space that we've got here, just because of the way that it works. So I'm going to start by drawing butan-2-ol. And I will give you a couple minutes after I'm finished doing this to copy it out. So butan-2-ol is an alcohol. So I've drawn 4 carbons for but, and then I've put my OH group on for my alcohol, and I've put that on the 2nd carbon because it's butan-2-ol. Now in my molecule, I'm numbering my carbons from right to left. So the carbon on the right hand side would be carbon number 1, and then 2, 3, and 4. Okay, right, so when we dehydrate this molecule, what we are going to do, as the name dehydration would suggest, is we are going to remove water from the molecule. So water is H2O, that's 2 hydrogens and an oxygen. And the way that we do this is we're going to remove the OH group and then a hydrogen from an adjacent carbon. So we can actually do this in 2 different ways. We could remove the OH group and then the hydrogen on the right-hand carbon, or we could remove that OH group and the hydrogen on the left-hand carbon. And we'll actually get 2 different products depending on which hydrogen comes off. And we wouldn't have any control in our actual doing of this reaction over which hydrogen would come off. We're going to get a mixture of products here. So I'm going to follow my arrow in 2 ways. And I'm also going to pop on the name of our reagent that we're going to use. So I'm going to use aluminium oxide. I always tend to use aluminium oxide because this used to be a reaction, like a little experiment that we would do in intermediate 2 chemistry. And we always done it with aluminium oxide as our catalyst, which is why I always use aluminium oxide. So let's have a look at what would happen if we remove the OH and then the hydrogen on the right hand side. So basically what's in my little green box. So all I'm going to do is I'm going to redraw that molecule, but I'm not going to draw on the molecules or the atoms that I circled in green. Okay, so that's going to leave us with something that looks like that. Now, if you look at the carbon on the right-hand side and then the carbon beside that, you can see each of those carbons are only making 3 bonds, which is not acceptable for carbon. Carbon has to make 4 bonds. So what will happen is we will form a double bond in between those 2 carbons. And we have now prepared our alkene. And this alkene specifically is butanene. Okay. Now let's look at what would happen if we removed water from the atoms that I've circled in blue. So again, what I'm going to do is I'm going to draw all of the atoms that aren't being eliminated. They're all going to stay exactly where they are. And what we can see is the 2 carbons in the middle are only making 3 bonds each. So that's where we will form that double bond. And what we've got here is but2ene. So if we were to do a dehydration of butan-2-ol, we would make a mixture of 2 alkenes. We would get but1ene and we would get but2ene. So I'll give you guys a couple minutes to make sure that you've got that diagram copied in, and then we'll go on to look at base-induced elimination from monohaloalkanes. Okay. Right, so if you don't get the full diagram copied in, like I said, you can just look at the notes that I'll pop up once the lesson is done. All right, so we'll go on now to look at our second type of reaction, which is a base-induced elimination from monohaloalkanes. So we'll start by saying a base-induced elimination is achieved by heating a monohaloalkane under reflux with an ethanolic base. Okay, so our reagent is an ethanolic base. Now, heating under reflux is a technique that we will look at actually doing once we get back into school and we can do some practical work. Okay, so don't worry too much about what heating under reflux means. We will actually have a proper look at that. So, an ethanolic base is usually potassium hydroxide or sodium hydroxide, so those are both bases, that has been dissolved in ethanol. Okay, so we don't dissolve the potassium hydroxide or the sodium hydroxide in water. It's not like potassium hydroxide solution or sodium hydroxide solution. It is potassium hydroxide dissolved in ethanol, or maybe even sodium hydroxide dissolved in ethanol. It wouldn't matter which one you used. Okay, and our example is a base-induced elimination of 2-chloropropane. Now, strictly speaking, we could just call this an elimination reaction, because ultimately that's what it is. All of our preparation of alkenes is by elimination reactions. But by using the full name of base-induced elimination, it gives us a clue as to what the reagent is that we use to do the elimination reaction. We use a base. That's why it's base-induced. So the elimination reaction is induced or brought on by the base, which is your potassium hydroxide or your sodium hydroxide. So for the example that we're going to look at here, there's just going to be one product, but do make sure that you check to see if there would be one or two products that are formed in the reaction. So base-induced elimination of 2-chloropropane. So the first thing that I'm going to do is I'm going to draw out 2-chloropropane. So because it's propane, that means we're going to have 3 carbon atoms, and 2-chloro means that there's a chlorine atom on the second carbon. And that molecule there, that's our monohaloalkane. It's an alkane that's got a halogen on it, one halogen. So halo meaning halogen and mono meaning one. Right, so to do this reaction, we are going to use this. For this one, we'll use potassium hydroxide. So I'm going to write in KOH, and then I'm going to use a little bracket and like a subscript with ethanol. Now, for this particular reaction, we are going to remove the chlorine and a hydrogen from a neighbouring carbon. So, in theory, we could remove the chlorine and the hydrogen on the right, or we could remove the chlorine and the hydrogen on the left. But no matter which one you do, you're going to end up with the same product. Okay? So there's only one possible product that we can get here. So if we look at the product, popping my double bond in between the carbons that I have eliminated the atoms from. And what we are going to end up with here is propene. Now, there is no such thing as like prop-1-ene or prop-2-ene. All propene is prop-1-ene because that double bond must start on the first carbon. And you're going to number your carbon chain from the side closest to the double bond. So if the double bond is where it is in that molecule, you've got carbon 1, 2, and 3. If you put your double bond on the other carbon, so let's say we put our double bond in here instead, when we number our carbons, it'll be 1, 2, and 3. So no matter which way you do it, your double bond's always going to be on carbon number 1, which means you're always going to have prop-1-ene. And because there's no such thing as prop-2-ene, we just say propene. We don't actually have to say prop-1-ene because there's no other possibility. Okay. So if you were, working in a lab and you had a client that asked you to make an alkene, these are the 2 reactions that you would be going to. You would be thinking, right, okay, I'm either going to dehydrate an alcohol or I'm going to do a base-induced elimination using a monohaloalkane. And depending on the alkene that was ordered, you would then look at what you've got in your kind of chemical store, and you would decide how you were going to go about producing the alkene that was requested. Okay. Right, so that's how we prepare alkenes. What we're now going to go on to look at is how we react alkenes. Okay, so reactions of alkenes. So there is really only one reaction that we do with alkenes, and it is an addition reaction, or to give it its full name, an electrophilic addition reaction. Right, so there are 4 main addition reactions, each involving a different type of reactant molecule being added. Now, these are reactions that we probably looked at National 5 level, but we've probably not really thought about them much since. So, the number of products produced by an addition reaction depends on the symmetry of the starting alkene So the symmetry of the starting alkene and the type of reactant molecule being added. Okay, so what we've got here are our different types of addition reaction. So if we add hydrogen, it's known as a hydrogenation. And if we use a symmetrical alkene, we get one product. And if we use a non-symmetrical alkene, we get one product. Now, if you're sitting there thinking, oh, like symmetrical alkenes, non-symmetrical alkenes, like I'm not really understanding that, don't worry, because I'm going to do an example of every type of addition reaction that we're going through here. If we add on a halogen, so like fluorine, chlorine, bromine, iodine, it's known as a halogenation. And if we use a symmetrical alkene, we get one product. And if we use a non-symmetrical alkene, we get one product. If we add on a hydrogen halide, like hydrogen chloride, hydrogen fluoride, hydrogen iodide, we are going to call it a hydrohalogenation. And we'll get one product with a symmetrical alkene and 2 products with a non-symmetrical alkene. And then finally, if we add a water molecule on, we would call it a hydration reaction. And if we use a symmetrical alkene, we'll get one product. And if we use a non-symmetrical alkene, we'll get 2 products. So you can see that if we use a symmetrical alkene, we are always producing the same product. We're always just getting one product. But if we do a hydrohalogenation or a hydration reaction with a non-symmetrical alkene, we're going to get 2 products. So we're going to look at each of these reactions in a wee bit more detail. So for our first example, we are going to look at hydrogenation with a non-symmetrical alkene. So I'll use this as a wee kind of point at which I can talk about some of the differences, or what is a symmetrical alkene versus a non-symmetrical alkene. And it literally is just, does it have a line of symmetry kind of down the middle? So a non-symmetrical alkene. So let's look at propene, which is a non-symmetrical alkene. And if we were trying to determine whether it was symmetrical or not, we would put a kind of mirror plane down the middle of the molecule. And what you can see is the atoms on the left of that line do not match the atoms that are on the right of that line. So we can see that it is non-symmetrical. Right, to this we are going to add hydrogen because it's a hydrogenation. So I'm going to add hydrogen, remembering hydrogen's a diatomic molecule, so it will always exist as two hydrogen atoms bonded together. And then with addition reactions, what will happen is the carbon-to-carbon double bond will break and will be replaced with a carbon-to-carbon single bond. All of the atoms that you already have will remain. And just to make this stand out, what I'm going to do is I'll pop the hydrogens that I'm adding in a different colour. And because we've broken the carbon-to-carbon double bond between that left and middle carbon, you can see that the left carbon and the middle carbon are currently only making 3 bonds each, which means that there is space for one hydrogen atom to be attached to each of those carbons. Again, I'll give you like a little moment to just make sure that you can get that copied down. And again, if I go too fast for you, do just refer to the notes that I'm going to post pretty much as soon as we're finished with this lesson. Okay, so when we use hydrogenation, no matter whether the alkane being symmetrical or non-symmetrical, we always get one product. Okay, and that's because it doesn't really matter where you put each of the hydrogens, because you're adding the same atom onto each of the carbons, you're always going to get the same product because there's no possible variation. Right, for example 2, we'll look at a halogenation with a symmetrical alkene. So the symmetrical alkene we are going to use is, let's look at the simplest one, which is ethene. So ethene is our simplest symmetrical alkene. Again, when we are looking at it, we can pop a line of symmetry down the middle, and you can see that you've got the same arrangement of atoms on the left and the right. So for this one, we are going to add a halogen. We could pick any halogen, so that's any group 7 element. And remember that all of our halogens exist as diatomic molecules, so there'll always be 2 atoms bonded together. So I'm going to go with fluorine for this. Now remember, the symbol for fluorine is a capital F, and it should look like a capital F. It should not look like a lowercase f. So if your capital F's and your lowercase f's do tend to look a little bit similar, do just make sure that if you are drawing anything with fluorine, that you take extra care to make the f's look like capitals. They will take off marks if they deem your f's to look like lowercase f's. Okay, so again, what we'll do is we'll start by breaking the carbon-to-carbon double bond and replacing it with a single bond. There's 2 hydrogen atoms attached to each of the carbons, so nothing's going to happen with them. And then what we're going to do is we're going to add on our 2 fluorine atoms like so. So if we use a symmetrical alkene, we're always going to get one product. And if we use a halogen, we're also always going to get one product. So only one possible product being produced here. Now our third example is a hydrohalogenation with a symmetrical alkene. So for this one, again, I'm just going to use ethene, keep it nice and straightforward. And we'll look at how we only get one product when we're using a hydrohalogen or a hydrogen halide. So again, we'll use ethene. And we are reacting that with a hydrogen halide. So I am going to use hydrogen iodide. Like so. So again, when we do our addition reaction, we are going to start by breaking the carbon-to-carbon double bond. Each carbon has 2 hydrogens already attached. So I will keep those two hydrogens attached. And now we have a choice. We could choose to put the iodine on the left-hand carbon, or we could put the iodine on the right-hand carbon. So if I put the iodine on the left-hand carbon and the hydrogen on the right-hand carbon, when it comes to naming this molecule, we would always number our carbons starting with the side closest to functional groups. And if there's no functional groups, it would be the side closest to any branches. Now the iodine is a branch, so that would make that carbon number 1, and that would be carbon number 2. Okay. Now if we chose to put the hydrogen on the left carbon and the iodine on the right carbon, then when we go to number, we will start with the carbon on the right because it's the one closest to the branch, the iodine branch. So that would be carbon 1 and that would be carbon 2. So you can see no matter which carbon you put the iodine on, it's always going to be on carbon number 1 in this case. And if we were looking at naming that, it would be 1-iodoethane. Don't worry too much about naming of haloalkanes because we have a kind of full lesson on that coming up in several lessons' time. But no matter what we do, the product there is always going to be 1-iodoethane. I'll give you a wee minute just to make sure that you have ample time to just make sure you've got those copied in correctly before I scroll to the next page. Okay, so let's now go on to look at some examples in which we could get more than one product. So example 4 is a hydrohalogenation with a non-symmetrical alkene. So again, I would probably just wait until you've seen this full diagram so that you can space it correctly, and I'll make sure to give you some time to copy it all in. So for my non-symmetrical alkene, I am going to use but1-ene. Right, so we're going to react that with a hydrogen halide. So we will use, let's use hydrogen chloride for this reaction here. So we're going to split our reaction arrow into 2 because for this particular addition reaction, there is going to be 2 possible products and we're going to look at them both. Right, so we'll start by breaking the carbon-to-carbon double bond and keeping all of the hydrogens that are already on but1-ene there. Okay, so we've got an option. We can put the hydrogen onto the first carbon and the chlorine onto the second carbon, or we could put the chlorine onto the first carbon and the hydrogen onto the second carbon. So for this one, I'm going to pop the chlorine onto the first carbon and the hydrogen onto the second carbon. Now, when looking at naming that molecule, we would start numbering with the carbon closest to our chlorine branch. And the name of that would be 1-chlorobutane. Then if we look at our second possibility, drawing the 4 carbons out again with the double bond broken. And this time what we're going to do is we'll pop the hydrogen on the first carbon and the chlorine on the second carbon. And that would be called 2. Chlorobutane. Now, I'll give you a wee moment just to make sure that you have hopefully had enough time to copy that diagram in. All right, now, the kind of interesting and maybe even somewhat unusual situation that we've got here is that you would probably expect that if we were to carry this reaction out in a lab, that there would be a 50-50 chance of the chlorine going on the first carbon as to it going on the second carbon. So you would probably expect that you would get 50% of 1-chlorobutane and 50% of 2-chlorobutane. When in actual fact, that's not what happens. What we end up with is a major product that you get 75% of and a minor product that you get 25% of. So the minor product is the 1-chlorobutane. And the major product is the 2-chlorobutane. And what we'll be doing in tomorrow's lesson is we'll be looking at why. Because a 75-25% split is far too much to be just chopped down to coincidence. There must be some kind of chemical reason that means that we get more 2-chlorobutane than 1-chlorobutane, and there is. And we'll be looking at how can we predict what our major product and what our minor product is going to be. And we'll also be looking at the chemistry behind why we get a major product and why we get a minor product. And it's to do with how the reaction takes place. And we will look at that, or start to look at that during tomorrow's lesson. And then our final example, example 5, is going to be hydration with a non-symmetrical alkene. So for this one, we'll use propane. And because we are doing a hydration with a non-symmetrical alkene, we will get 2 products. So when we do a hydration reaction, we are reacting with water, which is H2O, which will look something like that. Now, when we do our hydration reaction, one of the hydrogen to oxygen bonds will break. So we'll add a hydrogen onto one of the carbons where the double bond was, and the OH, the hydroxyl group, onto the other one. So what we'll do here is essentially we'll make an alcohol. So again, we're going to follow this reaction arrow across 2 paths. So starting as always by breaking the carbon to carbon double bond and then popping all of the atoms that were already present on the alkene onto our diagram. And then we are going to pop our hydrogen and our OH group onto the carbons where the double bond was. So I'm going to pop the OH group on that first carbon and the hydrogen on the second carbon. Now, when we have an OH group, that's a hydroxyl group, and that tells us that the molecule is an alcohol. We would always start by numbering the carbon atoms in the longest chain from the side closest to that hydroxyl group. So the hydroxyl group is on the first carbon. There's 3 carbons in the chain. So we are going to call that alcohol propan 1-ol. Okay. And then for the second possibility, we'll pop the hydrogen on the first carbon and then the OH group on the middle carbon. So when we are looking at numbering these, we find that the hydroxyl group is on the second carbon, 3 carbons in the longest chain, so that would be propan 2-ol. Now again, we get a major and a minor product. We don't get 50% propan 1-ol and 50% propan 2-ol. We find that our minor product is propan 1-ol, and that's 25%. And our major product is our propan 2-ol, and that is 75%. Again, I'm going to give you guys a couple of minutes to get that diagram copied in. Okay, so just to finish off, we've got in examples 4 and 5, there are 2 products produced in each of the reactions. You might predict that there would be an equal percentage of each product produced in each reaction, but in reality, there is a major product and a minor product. About 75% of the major product is produced and only 25% of the minor product. So the major product can be predicted using Markovnikov's rule and explained by using the inductive effect or using the inductive effect. Okay. Now, tomorrow we will look at Markovnikov's rule and the inductive effect. So what we will find that in the synthesis topic, and I've planned synthesis out to be about 15 lessons. I'll actually stop the recording just now.